Welcome to the lab. I'm your host, Trevor Smouter. In this episode of our PCB Stackup series, we'll explore the topic of transmission lines. I have two coax transmission lines with different ends. Can I use this F to BNC connector to join them together? We'll get to that answer in this episode of Startup Product Design. So why are we talking about transmission lines in our PCB Stackup series anyways? Whether we acknowledge it or not, every trace on a PCB is a transmission line. With careful planning, we can easily design circuit boards where all the traces are proper transmission lines. What is the definition of a transmission line? Let's go over to the whiteboard. A transmission line is a specialized cable or other structure designed to conduct alternating current of a radio frequency. That is, currents with a frequency high enough that their wave nature must be taken into account. So I have this coax cable. It's intended to deliver cable TV to your house. From the definition of a transmission line, we can assume that data sent on this cable is such that we must consider the wave nature of its electrical signal. Our startup product design understanding of the transmission line should be twofold. One, transmission lines help keep the signal from escaping during transmission. Ideally, all the power sent into the line will arrive at the far end. And two, unwanted or spurious signals will be prevented from corrupting the signal we are sending into the line. In this way, a transmission line is like a pipe that keeps desirable signals in and undesirable signals out. If we have a poor transmission line, then we'll have two problems. Our signal will leak out and noise will leak in. Before we get into the nitty-gritty of transmission line design and how it relates to PCB Stackup, let's give a nod to the black art that encompasses radio frequency or RF design. Remember that RF will challenge our notion of circuit sanity until we wrap our head around some of the concepts. And this relates to the statement in the transmission line definition with a frequency high enough that their wave nature must be taken into account. If we make a telegraph circuit with a switch on one end and a beeper on the other and send it a long distance, let's say across the ocean, when we close the switch, does the beeper start immediately? If we're just passing a current around from one side of the ocean to the other, it'll actually take several minutes for the beeper to turn on, and it would turn on really slowly as the current starts to build against the inductance of the line. So how do we get a signal across the ocean at a much faster speed? We use a transmission line. Let's think of this a little differently by applying a startup product design perspective. Clearly, we can send signals across the bottom of the ocean faster than one symbol every few minutes, so what gives? This is where the magic of transmission lines comes into play. Let's look at a coax cable to help understand how transmission lines work. Coax cables consist of a center wire conductor surrounded by a metal tubular conductor which are separated by an insulator. Having two conductors separated by an insulator reminds us of a capacitor. Watch our Back to Basics episode on capacitors if you need a refresher. We also know that every wire has inductance because it will establish a magnetic field around it when there is current flow. You might want to review our Back to Basics episode on inductance too. So a coax cable can be modeled as a wire, which is a sequence of inductors that also has capacitance with respect to the shield. Can we use this transmission line model to understand how signals can be sent long distances at much higher speeds than a conventional circuit topology we saw before? You bet. Let's go back to the whiteboard for a startup product design understanding of transmission line complexities. Say we take our transmission line and momentarily apply a voltage source. Current will ramp through the inductor and start charging the capacitance of the line. This will continue along the elements of the line. If we remove the voltage source, the inductance of the line works to oppose changes in current flow, which is cool because it makes the signal continue in a forward direction. The momentum of the current in the inductors creates the pressure required to fill capacitive buckets of charge in front of the propagating signal. The same momentum of current in the inductors also sucks the charge out of the capacitive voltage buckets behind the propagating signal, so that no charge is left on the line after the signal passes. This approach to sending a signal is really cool. There's a magic to it. I mean, since capacitors are used to transfer the signal from one end of the wire to the other, it's true according to Maxwell's equations that energy is flowing down the transmission line in the space between the conductors. So what happens when the signal gets to the end of the line? When the signal arrives at the end of the line, we can take the charge propagating down the line and have it dump into a load, such as the beeper at the end of our telegraph line. But what happens if we don't have a load attached to the end of the line? In this case, something weird happens. The inductors in the line continue to push the current forward until the capacitor at the end of the line reaches full charge. Because the power cannot be delivered to the load, the voltage at the end of the line starts the current charging back down the line in the opposite direction, eventually returning to the source. Now I know what you're thinking. There is some wackiness involved in how signals propagate down a transmission line, and it certainly challenges your concept of a circuit. But this is the stuff of black art RF design. Before we delve into the key aspect of this episode, let's look at one more interesting case on the whiteboard, the case of the shorted transmission line. In the case of a shorted transmission line, we still have nowhere for the signal to go at the end of the line, so we should expect that the signal will reflect back, and it does, but with a twist. Due to the short at the end of the line, the signal loops back around and charges the capacitive elements in a reverse polarity, so the returning signal is inverted. Now that we have a startup product design understanding of the function of a transmission line, let's talk about the details that need to be observed if we want it to work well. Remember that the capacitive elements and inductive elements work together to propagate the signal forward down the line. And this is critical. If the capacitive elements, which we can think of as voltage buckets, change size at some point along the line, then the buckets will be underfilled or overfilled, and this will upset the critical balance. This will result in some of the signal being unable to continue propagating forward, and it will be forced to turn back. A similar issue occurs if the inductive elements change at some point in the line. The resultant change in current momentum upsets the balance, and some of the signal will flow backwards down the line to the signal source. So it's critical that we maintain a consistent transmission line. In our maximum power transfer episode, we learned that we get maximum power transfer when the impedance of the source matches the impedance of the load. This is also true of transmission lines. If the impedance of two transmissions are different, such as in these two coax cables, which are 50 ohm and 75 ohm, then we'll get a significant amount of power reflected back when the signal reaches the interface between the two cables, even if we can find a connector to connect them together. If we think of the capacitive elements as voltage buckets and the inductive elements as current pipes, then it turns out that to maintain maximum power transferring forward down the transmission line, we need to ensure the voltage to current ratio of the signal on the line remains constant. And, as we saw in the maximum transfer episode, the voltage to current ratio is the resistance. So says Mr. Ohm. So why are we talking so much about transmission lines? I mean, do we need to design transmission lines? In the next episode of our Stackup series, I'm going to show you how easy it is to design proper transmission lines for our circuit board designs. It turns out that transmission line design is a critical factor when deciding what your board stackup should be. I hope you've learned something new in this transmission line episode, and I encourage you to keep following along in the series, and maybe even consider subscribing to our channel. Remember, you can design products too. Knowledge leads to success in startup product design.